we're doing is trying to get the key parameters that'll allow us to predict creep lifetimes of these nuclear reactor steels using indentation. So we're going to look at 4 different materials today. 2 of them are based on this grade 91 type of alloy, which is a ferritic martensitic steel. There's 2 different states that we're going to look at it in. One is the typical normalized and tempered microstructure that you see here, which is characterized by these kinds of lath structures. And then we're going to look at what we call high martensite grade 91. This is a similar material chemically to what is in the normalized and tempered state. It's just not tempered. And so we have increased fraction of martensitic lath. It's a harder material with a finer microstructure. We'll also be looking at 2 different types of Fekrol alloys, APMT and APM, which are both Kanthal alloys. We'll get more into what these microstructures look like in a moment, but the thing to take home here is that the grain size for the Fekrol alloys is very large. So we're looking at things where these are probably several hundreds of microns wide and even longer from the rolling direction. So we're going to be looking at kind of a composite sort of a response with the normalized and tempered grade 91, and then more of a single crystal response from the Fekrol alloys. The overall idea is to use instrumented indentation, and I'm not saying nanoindentation here. I'm doing that on purpose. If you notice, the scale bar here is fairly large. We're 5 microns. We're going to be doing essentially microindentation, but we use the features of instrumented nanoindentation to be able to do things like continuous measurement of X. In our case, we're looking at stiffness and getting continuous hardness profiles as we go deeper and deeper into the material. So we use those techniques to be able to then do things like strain rate jump tests, which Dr. Stauffer mentioned in his talk. These are tests where we can jump the strain rate from one strain rate to another, and as we go faster and faster, the strain rate or the stress associated with deforming that material goes up. These are the types of tests that have been done for a long, long time on bulk types of materials. Only in the last dozen years or so have strain rate jump tests been used extensively in nanoindentation. And so we're going to try to get things like the strain rate sensitivity, activation energy, and identification of the dominant mechanism, feed those pieces of information into a model, and use that model to predict things like the rupture lifetime. So we're trying to get to the fidelity of data that you would get from a large bulk creep test type of data set, but with a minimum number of bulk creep tests. What you're going to find here is that you can actually inform this model most of the way using nanoindentation data. So as I mentioned before, these types of tests doing strain rate jumps have been done for a long time. This is an example of what would happen in a compressive stress state. And so as temperature goes up, we end up having a decrease in elastic modulus, strength goes down. And so by just doing a few tests, strain rate jump tests, we can get data for a wide range of temperature and strain rate. And so as we increase strain rate, we increase the flow stress, we increase temperature, decrease the flow stress, decrease the elastic modulus. And from these types of relationships, we can get things like activation volumes, activation energies, strain rate sensitivities, and so forth. These become important when we look at something like the constitutive equation for steady state creep, which is also known as the Mukherjee-Bird-Dorn equation. It consists of having the strain rate, which is dictated by a constant A times your applied stress raised to a stress exponent N, divided by the grain size of the material raised to a grain size exponent lowercase q. We have a fairly weak temperature term out here in front of the exponential, and then the exponential contains activation energy and then kT. So we have a stronger temperature term in the exponent. So we can find that strain rate sensitivity, which is simply 1 over this n parameter, looking at the change in the log of stress relative to the change in the log of strain rate. So we can get that from each of the jumps that we do within a test. We calculate that we have a constant strain rate during each of our jumps using this relationship that the strain rate in indentation is equal to 1/2 of the loading rate over the instantaneous load. And so using this information, if we identify the critical parameters, such as our stress exponent n, we can start looking at things like deformation mechanism maps, where if we plot normalized stress against normalized temperature, power law creep, which we'll get into that mechanism here in just a moment, has a stress exponent of about 3 to 10. Diffusion-based creep usually has a stress exponent closer to 1. So by measuring those stress exponents, we can identify the creep mechanism that is dominant at those conditions, and we can then use that information to predict its behavior. So it's important to know that if we plot just creep strain versus time, if this were just a uniaxial test, if we increase stress and temperature, we end up having a transition in what our creep curve looks like, as you can see here on the left. So we're going to be looking at two types of creep deformation, primarily one in the test regimes that we did here. Diffusion-based creep is based solely on mass transport by diffusion. So if we pull on a material, we get a Poisson contraction in the horizontal direction. Our vacancy flux ends up resulting in mass flux towards our tensile axis. And when we do that, we end up with a little bit of grain boundary sliding that has to be accommodated by dislocation motion. But the bulk of material that's moved in diffusion-based creep is by diffusion itself. And then power law creep is a completely different mechanism where we have a source for things like dislocations. Dislocations then glide along on a slick plane until they hit an obstacle and then have to climb around it. The rate limiting step here is climb. And so it ends up having a higher stress dependence because it's dislocation based than what we would see for diffusion based creep. So we have a stress exponent somewhere in the realm of 4 to 10. Now, if we're just at a little bit lower temperature than where we usually see creep mechanisms, we can also see the mechanism known as dynamic strain aging, DSA.